Final system overview. Volcanic eruptions are one natural disaster that poses significant threats to communities, causing destruction, loss of life, and environmental hazards. One of the challenges during an eruption is detecting its intensity and heat distribution in real time to provide timely evacuation guidance for affected populations. Our mission is to develop a CubeSat that is capable of detecting volcanic heat signatures from space, allowing for rapid assessment of eruption severity. By analyzing thermal data, our system can help authorities make quick, informed decisions on evacuation routes and emergency response, ultimately minimizing casualties and improving disaster preparedness.
This is our CubeSat prototype operations. So as you can see here, the lava is coming down, and this is sort of what our demo looked like as we took the test for our CubeSat. Now these are our ground station operations. Our ground station operation is where we send the code to the CubeSat and we receive an output. And we start this code by first setting the start command to the CubeSat, and it usually will take pictures as it moves, but because of this setup, we did put a different method of taking the pictures where we would just click enter and it would take the pictures for us. So as it will go over the volcano, it'll take a succession of pictures between 2-second intervals, and the original pictures will be also sent to us with the pictures, but a mask will also be sent to us indicating a potential volcanic event or an extremely high increase of temperature on the surface. In addition, depending on where the white spots are on the mask, it will print direction the lava is based on the 8 units of direction. As you can see right here, it'll print either north, northeast, east, southeast, south, southwest, west, or northwest.
To simulate volcanic eruption, we created a small-scale model representing a volcanic region. Using clay and plaster, we sculpted a mountain to represent the volcano, shaping its structure to resemble real-world volcanic formations. To replicate an eruption, we prepared an empty plastic bottle as a chamber inside the volcano and filled it with a mixture of yeast, hydrogen peroxide, and soap. This chemical reaction produces a foamy overflow that mimics real lava flow, demonstrating the spread and impact of volcanic activity. We placed the CubeSat above the volcano to get an image of the eruption.
The results were amazing. Our demo showed that the white areas under the mask were spilled with lava. As the CubeSat would send pictures to us, we could analyze which directions the lava would go in and make sure to notify nearby areas of a potential hazard. We would receive an image of the CubeSat that the CubeSat took originally and its mask over it, as well as to make sure we could oversee any errors. However, the CubeSat may give wrong directions depending on which direction the CubeSat itself is facing in, and also if the lava is not matching the color temperature threshold, it may also produce false reports. One thing we definitely can do in the future is include AI modeling to predict the path of the lava for us.
Some changes that we would like to make in regards to our prototype are the durability of the satellite casing, the imaging system, and the power source. First, the CubeSat's casing should be constructed with the more heat-resistant and impact-resistant material to withstand the harsh conditions of space. Second, the imaging system should be upgraded to a high-resolution camera with thermal imaging capabilities to better capture volcanic activity. Lastly, the battery should have a higher energy capacity and the solar panels should be optimized to maximize energy capture and efficiency to ensure sustained operation in orbit.
It is important to plan on building the CubeSat until we're finished, since small defects may cause massive damage or even failure of the mission. We used 3D modeling to visualize our CubeSat so we can review and plan when we were meeting. We went through lots of trials and errors during our test phase. However, we eventually made it work by trying all ideas from each member, no matter how they sounded, whether difficult or not. We were able to see if the ideas are practicable or not as we performed more trials. This process actually helped us in later situations, such as creating a simulation, since it helped to keep our mind open and share more ideas that could be feasible. For future CubeSat missions, communication should be done well before moving on to real actions, because in order to be successful, it is important that members keep sharing their own perspectives, or developing and improving the CubeSat would be really difficult.